We've already briefly discussed the use of binary in digital systems, but I wanted to go into a little more detail and talk about the underlying mathematical foundation and to make sure that we're all on the same page of converting between binary and decimal. Okay, so why do computers use binary? Well, because we've talked about this. There are basically two states. This comes from the fact that we have transistors that turn on and off. And so you can have a high level represent a 1 and a low level represent a 0. And we've talked a little bit about how this gives you some noise margin so you get more reliable computing. Decimal, that would require 10 levels, a level of complexity that is just not practical for how we design digital systems. So everything becomes bits. We've also talked about how you can represent other types of information like text using a binary code. The same thing can happen with images. Images can be quantized into pixels. Pixels have values. There's a red channel, a green channel, and a blue channel. Each pixel has a certain value across those channels. So bits are everywhere. And so it's important for us to understand how we use binary in different contexts. So what we're going to do today is we're going to look more about the underlying math that supports representing numbers with binary. Okay, so you probably already know this, but let's go through it. When we have a binary number, we can use binary to represent the traditional decimal number. And we do that very similar to the way we do decimal. Decimal has place values, powers of 10, that we use to represent a count for a given number. All right, so let's go through this example. And by the way, I've given you several examples that you can work through, so you can have access to this graphic and play with these examples yourself. Okay, so first of all, let's look at the binary digit or binary number 1101. All right, so what we do here is we have a weighting on each of the places. It's a positional system. The first to the rightmost place is the 2 to the 0's place. Then we have the 2 to the 1, 2 raised to the second, 2 raised to the third. So basically the 1's place, the 2's place, the 4's place, and the 8's place. So if I have 1101, then what I'm looking at is the addition of 8 in the most significant bit position with 4, followed by 0 times 2, so that's 0 contribution, and then 1 times 2 to the 0, which would be 1. So you add all those things together and you get the decimal equivalent of 13. Okay, so you can go through another example. This one has 5 bits, and so it's 2 to the 4th as the most significant place. So that's the 16th place. And so as you step through that, that would be 16. And there's a 0 contribution from 8, and then 1 from 4, 1 from 2, and 0 from 1. So you add all those numbers together, and you end up with 22 decimal. So I think that's a pretty straightforward direction. The direction that people sometimes get a little confused on, turned around on a first exam, is the other direction, going from decimal to binary. It's pretty easy, but if you haven't practiced it and it hits you as an exam problem, sometimes people panic a little bit and have trouble with that particular kind of problem. So let's work through it. There's a couple of methods that you can use here. One method is the division method. So we take a decimal number like 13 divided by 2, and basically what we're looking for is remainders. Okay, so 13 divided by 2 is 6. 6 times 2 is 12, so we have a remainder of 1. Okay, so we write that down. And then we take that 6 and we divide that by 2, and we get 3 with a remainder of 0. And then we take that 3 divided by 2, you get 1 with a remainder of 1, and one final step, 1 divided by 2 is 0 with a remainder of 1. So you can think of reading up from there to get the binary equivalent. And so read the numbers from the bottom to the top, and you end up with 1, 1, 0, 1. Okay, not a surprise, that's what we did before. So let's run through that second example again. Before we'd done a 22 in binary, let's check how you would go back from decimal to binary. All right, so our next step here would be take the number 22 divided by 2, you get 11 with a remainder of 0. Take the 11 divided by 2, you get 5 with a remainder of 1. Take the 5 divided by 2, you get 2 with a remainder of 1. Take the 2 divided by 2, you get 1 with a remainder of 0. 1 divided by 2 is 0. Then you stop. That has 1 with a remainder of 1. So you read your way up from there, and you get the answer that you expect. Okay, there's another way that you can do decimal to binary conversion, and I find myself doing this method mentally more often than the divide by method. Okay, so let's talk about that. Let's go with a bigger number like 37. Okay, so what I'm thinking here is that you have 37, and so you're starting to look at pushing powers of 2 that are smaller than 37. So 32, 2 to the 5th is 32. So you're asking yourself the question, does 32 fit into 37? And yes, it does, okay? And then so from there, you just subtract the difference. And because it fit, you have a 1 in the 32nd place, okay? So then you ask yourself, does 16 fit into 5? It does not, okay? So we'd write down a 0 and keep the 5, okay? So does the next power of 2 down 8 fit into 5? Nope, so there's yet another 0. Does 4 fit into 5? Yes, it does. 5 minus 4 is 1. So we write down the 1 because it fits in. Then we take the 1 and say, does 2 fit into 1? No, it does not. So we keep that. Does 1 fit into 1? Yes, there's no remainder. Because that difference is 0, we're done. And from there, we can just read the bit positions. This time you'd go down because you've got the order, most significant bit down to least significant bit. So as you read this would be 1, 0, 0, 1, 0, 1. So it goes the opposite. It goes down instead of up like we did with the divide by method. Okay, so those are a couple of techniques. It gives you the mathematical foundation because with the positional system, we're going to use this, and I think we use it enough where it becomes second nature.